the impulse and momentum topic. This section, 5.2, is a basic introduction to momentum and change in momentum. Now, what I will not be doing in this video, I will not be going into the relationship between impulse and change in momentum. That will come in at least the next 3 videos after this. This is going to be very, very simple, right, basic momentum, and very, very simple, the equation, the symbols, etc., for calculating change in momentum. It's going to be very, very, very simple, basic momentum and change in momentum. So, we need a definition for momentum. Now, technically what we're talking about here is linear momentum. We will not be talking about angular momentum. All right, so since we won't be talking about angular momentum, we're just going to call it momentum. All right, so momentum is the product of an object's mass and its velocity. So momentum, right, and the symbol is the Greek letter rho. All right, so this is a lowercase Greek letter rho. Now most people are just going to put a regular lowercase English p, all right, but it technically is rho, is equal to mass times velocity. All right, now what I'd like to do now is take a very simple example. Let's look at a tractor trailer, okay, a fairly relatively large object with a lot of mass. Okay, here's the tractor, all right. There's the wheels in the front, there's the wheels on the tractor in the back. Okay, we got that. And now here's the trailer. All right, there's the trailer in the back. And we've got some axles and such to level that off. And we've got some sets of wheels in the back there. Okay, so here's the tractor, here's the trailer. All right, and that is about 8,154, all right, kilograms. All right, 8,154 kilograms. Okay, which is about 18,000 pounds. All right, but we won't be working in pounds, we're working in the metric system. All right, now what I'd like you to tell me, I'd like you to describe the inertia that this truck has. Oh, and by the way, okay, this truck, we have to say, is at rest. All right, the truck is at rest. So the mass of the truck we know, 8,154 kilograms, and the velocity of the truck we know is 0 meters per second because the truck is at rest. Now, I'd like you to describe the inertia, right? Relatively speaking, is it large or small? And I'd like you to describe the momentum that this truck has when it is at rest. Is it large, is it small, or something else? Okay? So I hope you remember that inertia is based only on mass. So we can say that this truck, because it has a relatively large mass, it has a relatively large amount of inertia. Now remember, there's no equation for inertia, there's no symbol for inertia. Perhaps you can think of it as more of a concept than a physical quantity. All right, but in any case, the truck has a lot of inertia because it has a lot of mass. Now, momentum, on the other hand, is based upon mass and velocity. And since you're going to multiply them together, anything that you multiply by 0 is going to be 0. So this truck has 0 momentum. All right, so inertia is based only on mass. This truck has a very large inertia. But momentum, which is the product, you multiply the mass and the velocity together. Since this truck is at rest, and anything you multiply by 0 is going to be 0, this truck has 0 momentum. All right, now let's take a look at the quantity momentum. Let's look at its symbol, its equation, all right, the equation that defines momentum, and let's derive the unit from the equation. All right, so the quantity that we're looking at is momentum. All right, the symbol we know is the lowercase Greek letter rho. All right, a lot of people are just going to put a lowercase English p. The technically correct symbol is the Greek letter rho. All right, the equation, all right? Rho equals m times v. Momentum equals mass times velocity. Now, let's derive the unit. Derive means figure out. Let's figure out the unit based upon the equation. All right, the unit for momentum would be equal to the unit for mass, the kilogram, times the unit for velocity, meter, all right, per second. So you've got kilogram times meter on top, per, see the per, P-E-R, all right, per second on the bottom. All right, so the unit, I'm going to move it over there where it says unit. All right, the unit is the kilogram meter per second. We could write that out. Kilogram meter per second. If I had the room, I would write that all straight out on one line. All right, so now let's calculate the momentum of that truck that we were just talking about. All right, so the equation, okay. All right, so we were given information about the truck. We were told that the mass of the truck is 8,154 kilograms. We were told that the velocity of the truck is 0 meters per second. They said the truck was at rest, so the velocity is 0 meters per second. We are asked to find the momentum, all right? And the correct unit for that would be kilogram meter per second. Okay, there is no special name for kilogram meter per second. It's just kilogram meter per second. All right, so now we pick a formula, right? Given, find, formula. We pick a formula that has, hopefully, momentum, mass, and velocity. So, all right, momentum equals mass times velocity. All right, let's move that over just a little bit. All right, momentum equals mass times velocity. Okay, so the mass is 8,154 kilograms. Remember, you have to put the units when you substitute. The velocity is 0 meters per second. All right, and that means whatever we've got here times 0 is going to be 0. All right, so the momentum of the truck is 0 kilogram meters per second. All right, the momentum of the truck, now we'll put it over here, is 0 kilogram meters per second. Very simple, basic calculation of momentum given the mass and the velocity of the object. All right, now at this time I'd like to mention that momentum is a vector. Now, how do we know this? Well, anytime you multiply a scalar, all right, times a vector, you're going to get, your answer is going to be another vector. Let me give you some examples that we've already covered. All right, displacement, all right, d would be equal to time times velocity. All right, displacement would be equal to velocity times time. I just switched them because time is the scalar, all right? So when you multiply a scalar like time times a vector like velocity, you're going to get another vector, right? This is always going to be a vector over here, all right? Let's look at another example, all right? Force is going to be equal to mass times acceleration, okay? So we multiply a scalar like mass times a vector like acceleration, we get another vector. We know that force is a vector. Force equals mass times acceleration. All right, just putting the equation together over there. All right, impulse, which you may have already covered. All right, I did cover it in 5.1. All right, impulse is going to be equal to, all right, force times time. And I'm just going to flip them around so that the scalar is first. All right, force times time. All right, impulse is equal to force times time. You're multiplying a scalar by a vector, you get another vector. All right? And finally, what we're talking about today, all right, momentum is going to be equal to mass times velocity, right? Momentum is equal to mass times velocity. All right, so what we're looking at here is 4 different examples when you take a scalar and multiply. This is regular multiplication, all right? You take a scalar and multiply by a vector, all right? You automatically get a different vector, all right? And by the way, okay, the direction of the vector, the original vector, right, is the same as the direction of the new vector. So whatever direction this vector is the same direction. Whatever direction the acceleration is here, this force is in the same direction. Whatever the direction is of the force, this impulse is in the same direction. And finally, for what we're doing right now, momentum, whatever the direction of the velocity is, the direction of the momentum is the same direction. Okay, so momentum is a vector. Remember, impulse and momentum, the name of the topic, they're buddies and they're both vectors. Impulse and momentum are both vectors. So, we've established that momentum is a vector, and as a vector, it has to have a magnitude and a direction. Now, a moment ago when we calculated the momentum of the tractor-trailer, it came out to be 0, so there was no direction. All right, but then let's take a look at Raphael and Rihanna. Raphael, his mass is 50 kilograms, is walking east at a velocity of 3.0 meters per second. His twin sister Rihanna, also 50 kilograms, is walking west at a velocity of 3.0 meters per second. And the question is, are their momenta equal? Well, let's calculate the momentum of Raphael and Rihanna's momentum as well. All right, so nice and simple, mass times velocity. All right, momentum is equal to mass times velocity. We'll do Raphael first. We'll call him the boy. Okay. All right, so his mass is 50 kilograms. Now, since his velocity is 3 meters per second east, we're going to make that positive 3 meters per second. All right, and so the answer that we're going to get, the momentum for the boy, all right, is 150, all right, sorry, positive 150 kilogram meters per second. All right, now, what about Rihanna, all right, the girl, okay? Her momentum of the girl, all right, we'll just put momentum G, okay, is her mass times her velocity, all right? Her mass is 50 kilograms, but her velocity is west, so we'll put negative 3.0 meters per second. Okay? East is positive, west is negative, so her momentum is going to be negative 150 kilogram meters per second. All right, so the question, are their momenta equal? The answer is no. You cannot say that positive 150 is equal to negative 150. This is a vector. Momentum is a vector. So in order for them to be equal, both the magnitude and the direction would have to be equal. Now what you can say, all right, and I think we'll erase over here, okay, what you can say, all right, are their momenta equal? No, comma, the magnitudes, right, the 150 and the 150, all right, the magnitudes of their momenta, that would be plural, the plural of momentum, all right, the magnitudes of their momenta are equal, comma, but the directions are opposite. All right, so you cannot say that these two, positive 150 and negative 150, are equal. You can say that the magnitudes, meaning the number, right, the absolute value, 150 and 150 here, you can say the magnitudes are equal, But you would have to add that the directions, positive and negative, right, for east and west are opposite. Now, if you like, you could also report this, right, as, just erase that, you could report this as his momentum is 150 kilogram meters per second east, all right, positive or east, pick one, okay, and you could report this one, all right, the negative, you could report as the momentum for the girl is 150 kilogram meters per second west. All right, so either negative or west, all right, don't put both, all right, never put, I'll show you what never to put. Never put, for example, that the momentum for the girl, all right, is negative 150 kilogram meters per second west. What you're saying is the west and the negative are going to cancel each other, and the answer would be wrong. So you're going to pick either west or negative to indicate the direction, all right? Positive or east, all right? Negative, I'll put that one over here, all right? Negative 150 kilogram meters per second, all right? Positive or east, negative or west. So, let's see if you understand about momentum. Which one has more momentum? A 25 kilogram cannonball or an 8,154 kilogram truck? Which one has more momentum? It's easy, right? I'm glad you said, look lady, I can't tell you which one has more momentum because you haven't told me the velocity of either of the objects. Momentum depends on mass and velocity. Right now, we can't tell. Okay, now let's do this right. Which has more momentum? A 25 kilogram cannonball fired with a velocity of 200 meters per second to the right, or an 8,154 kilogram truck traveling with a velocity of 0.5 meters per second, also to the right. So all you need to do, right, is take the mass times the velocity. All right, 25 times 200 is going to give us 5,000. So the momentum, right, for the cannonball, we'll put momentum C, right, is going to be 5,000. Right, that's positive. We're going to the right, so it's positive. The momentum of the cannonball is positive 5,000 kilogram meters per second. Okay, we just multiply the mass times the velocity, and the direction of the velocity to the right, is the same direction as the momentum. I'm going to put positive, meaning to the right. Okay, and here, the mass times the velocity for the truck, 8,154 times 0.5, all right? So the momentum of the truck is also to the right, so it's positive 4,077 kilogram meters per second. All right, so in this case, the cannonball, because it's going so fast, has more momentum than the much more massive truck, which is traveling slowly. Right? It depends, momentum depends on the mass times the velocity. Remember, you have to indicate the direction in your answer. To the right would be positive. To the right is positive. If it was to the left, you would put a negative in front of here. All right? If it was to the left, you would put a negative in front of the answer. If the velocity is positive, then the momentum is positive. If the velocity is negative, then the momentum is negative. Now I'd like to start talking just a little bit about change in momentum. We find that the momentum of an object can change if either its mass or velocity, or perhaps both, changes. Let's take the example of a man. He walks over to a 30 kilogram shopping cart, initially at rest. He gives it a push, and now the shopping cart is traveling at 2 meters per second to the right. Let's calculate the momentum of the shopping cart before the man pushes it, when it is at rest, and then calculate the momentum of the shopping cart after the man pushed it, and now it's traveling at 2 meters per second to the right. So, momentum initial, okay, is going to be equal to the mass times the initial velocity of the shopping cart. The mass of the shopping cart is 30 kilograms. The initial velocity of the shopping cart is 0. The shopping cart is at rest. So 0 meters per second. So the initial momentum of the shopping cart is 0, right? 30 times 0 is 0 kilogram meters per second. What about the final momentum of the shopping cart? The mass of the shopping cart stayed the same, the velocity of the shopping cart changed, and now the shopping cart has a different momentum. Momentum final, right, see the little f, is equal to the mass of the shopping cart times the final velocity. Right, the mass is still 30 kilograms. The final velocity is positive, it's to the right, 2 meters per second, positive 2 meters per second, all right, and 30 times 2, all right, the final momentum of the shopping cart is positive 60 kilogram meters per second. All right, so the momentum of the shopping cart changed. Initially, the momentum was 0, and now the momentum is 60. Let's look at the symbols, the unit, the equation for change in momentum. All right, so the quantity we're looking at now is change in momentum. Now, a symbol for change would be the Greek letter delta. All right, delta means change. Change in momentum would be delta rho. Change in momentum. Now, whenever you do a change, it's going to be final minus initial. Let me give you a slightly different example that perhaps you know already. All right, change in temperature would be the temperature final minus the temperature initial. Okay? In science, we like to do final minus initial. Okay? Final minus initial is accepted for any change. So, the change in temperature is temperature final minus temperature initial. So the change in momentum is going to be momentum final minus momentum initial. Now, let's show that another way. All right? The change in momentum, instead of momentum final, we can put mv final, because mv final is the same as momentum final. This equals that. All right? Now, minus, right, mv initial. Now, this is assuming that what's changing is the velocity of the object. Generally speaking, we're not going to do problems where the mass of the object is changing. The masses of most objects tend to stay about the same. Right? If a few pebbles fall off the back of the truck, right, we're not going to say that the mass of the truck changed because it's so small with respect to the 8,000 kilograms for the truck. Now, one very good example of a mass that changes is when a rocket goes up into the air. The fuel is being burned and coming out the bottom as exhaust. So the mass of the whole rocket, because the fuel is coming out the bottom, the mass of the rocket is actually decreasing as the rocket goes up. But again, there aren't too many great examples where something's mass is going to change. If we're talking about people, their mass is not changing, for example, while they're playing baseball. If we're talking about a car, the mass of the car is not changing appreciably as the car is accelerating. Right? So generally speaking, it's going to be the velocity that is different at the end than it is at the beginning. V final, V initial. The two M's oftentimes are the same. So another thing that you could do is you could say delta rho. Remember, that's rho, not P, all right? I'm going to factor out the M, right? And then V final minus V initial. Okay, so we've got all kinds of symbols here. Delta means change. Rho means momentum. The change in momentum is equal to the final momentum minus the initial momentum. Nice and simple, all right? The change in momentum is equal to mv final minus mv initial. That's the same. This is also the same. The change in momentum is equal to factor out the m times the quantity v final minus v initial. All right, now, the unit. When you subtract, the unit stays the same. If I had, for example, 7 oranges, and I subtracted 4 oranges, I would get 3 oranges. When you subtract or add, the unit stays the same. So the unit for change in momentum is going to be the same as the unit for momentum. It's going to be our old friend, the kilogram meter per second. Okay? Back to the guy with the shopping cart, because it's a nice simple problem and we can do change in momentum and you can start to get used to calculating change in momentum. So if we're going to calculate the change in momentum for the guy with the shopping cart from the previous problem, all right, change in momentum, let's put it right here. Change in momentum is equal to mv final minus mv initial. Now, if you remember, the initial velocity of the shopping cart was 0. So if that's 0 and you multiply by m, this m goes away. So that goes away. So what we find is that when the initial velocity of an object is 0, all right, then the change in momentum is equal to the final momentum. Because this would here be 0 anyway. Okay? So we would simply put in 30 kilograms. Remember the shopping cart? Go back and look at the notes if you forgot the numbers, okay? 30 kilograms, all right? And the speed of the shopping cart, I should say the velocity of the shopping cart, was 2 meters per second to the right. So the change in momentum, in this case, is the same as the final momentum. It is positive 60 kilogram meters per second. All right, now what's going to happen in just a moment is the man is going to start pushing the shopping cart faster. And we're going to calculate the change in momentum when he pushes it faster. You can think of this as a totally brand new problem. The man is pushing the 30 kilogram shopping cart at 2 meters per second to the right when it starts to rain. He wants to reach his car faster, so he pushes harder. He increases his velocity to 5.0 meters per second to the right. And we want to know the change in momentum from a velocity of 2 meters per second to a velocity of 5 meters per second. All right, so here we go. All right, change in momentum is going to be mv final minus mv initial. All right, now in this case, since nothing is going to drop out, we can save ourselves a little teeny bit of time by factoring out the m and then doing v final minus v initial. All right, so m is 30 kilograms. The mass of the shopping cart is 30 kilograms. Now, be careful here. V final is 5. V initial is 2. So it's 5 minus 2. V final is 5. All right, and for that matter, it's positive 5. All right, 5 meters per second minus 2 meters per second. Okay, so 30 times 3. All right, 5 minus 2 is 3. 30 times 3, all right, is 90 kilogram meters per second. All right, and that's positive. All right, so let's write that down here. The change in momentum is positive 90.0 kilogram meters per second. Be very careful that you get V final right, V initial right. Make sure it's final minus initial. Don't write initial minus final. That would be wrong. If it's to the right, it's going to be positive, positive. Okay, there's a minus sign there, but you're plugging in a positive and a positive. We're going to be doing more complicated problems in later videos where objects are starting to the right and then having a velocity to the left, or they're starting to the south and then they have a velocity to the north. All right, but for now, nice and simple. I hope now you understand momentum and change in momentum.